What's going on, everybody? This is Mr. Diamond, and welcome to the introduction for Chapter 2 of Physics, 2D Kinematics. Just as a quick refresher, and I'm sure you guys don't need this, but just in case, vectors are quantities with magnitudes and directions, while scalars are quantities with no directions. And we're going to be getting into questions and equations involving adding and subtracting these things, so it's important to keep these ideas in mind, because vectors will need to be kind of singled out because their processes will be a little bit different. To do that, we'll usually place an arrow above the letter term for that vector. So like displacement, you may see it written as like a D with a little arrow over the top. Velocity, same thing. Velocity with a little arrow over the top. I usually won't do that just because it's kind of like, it's just an extra step and it's easy to forget. So I won't blame you if you don't do it. I just want to make sure that you've seen this. So if you watch videos or if you go out and look anywhere else, or if you take any future physics classes, you'll recognize that this is identifying it as a vector. And if you remember the clip from Despicable Me, he talked about it's a mathematical symbol represented by an arrow with both magnitude and direction. So if you're doing scalar addition, it's not very difficult. You just have to add the numbers together. But adding vectors requires a new method unless they happen to have the same direction, like if they're only in the x direction or only in the y direction. So very easy examples would be you move 5 kilometers to the east and then 3 kilometers to the east. So if we think north, east, south, west, so 5 to the east, 3 to the east, we just add them together. 5 plus 3 is 8 kilometers. Again, it doesn't specifically list a direction, but the fact that it's positive is telling you it's to the right. And then moving 5 kilometers to the east and then 3 kilometers to the west. West is implied to be the negative direction because it's moving to the left, so it's 5 plus negative 3 is 2 kilometers worth of displacement. So the vector would be 2 kilometers or 8 kilometers in these two examples. However, what would be the displacement if you were to walk 10 kilometers to the east and then 5 kilometers to the north? This problem involves more than just adding your components or subtracting your components together, because you're now in both of the directions. You're in the x area and you're in the y area. So you have to get a little bit more creative. And those of you who are really into math may have already figured out a direction that we could go to figure this out. And you're thinking, this isn't that hard of a problem. But you're right. We're just using this to kind of explain how we will apply this concept to later problems. So in this example, we're moving a certain amount this way and then a certain amount this way. And if you notice, our total displacement would form a triangle. So graphically speaking, we could draw our two vectors as arrows and then form a triangle made out of our two vectors. And because this example makes a triangle, we could just use the Pythagorean theorem, a squared plus b squared equals c squared, where c is the hypotenuse of this right triangle right here. It's going to be this long side that we made. So for this example, a squared equals 10 squared plus 5 squared, or rearranged, we will get basically about 11.2 kilometers. In this example, we have a total displacement of 11.2 kilometers. Notice this is not the sum of the parts because they weren't going in the same direction. In fact, I mentioned this last chapter, this will always be the case. Your total displacement will always be less than or equal to the sum of all of the displacements that occur over the course of a journey or a trip or whatever you're talking about. You can't travel, just like with distance, you can't travel 15 meters worth of distance and have 30 meters worth of displacement without wormholes or something weird like that going on. Now, this method that we use to just get to the Pythagorean theorem is called the tail-to-tip method of vector addition, because scientists are the most creative sort of people you will ever meet. And technically, you can use this method for any number of vectors being added together, but that usually just ends up being more complicated because you'd have to draw all the arrows to scale, and I don't know about you, but I wouldn't have to trust myself to like get out a grid and like draw them to scale. But in this case, let's say we have 3 separate occurrences or 3 separate like legs of a journey. All we would do is take their individual vectors. We don't even technically need to add them in order. We could add them in whatever order we want them to, and then we just put them tail to tip. And then we add the next one. That tail goes attached right to the very tip of the previous vector, and then we do it to the next one. So notice if we would have put A up here, and then B here, and then C here, we would have ended up in the same location. And then to describe your total vector, in this case, the vector of C with an arrow over its head, A with an arrow over its head, and B with an arrow over its head, you would describe it as 50 meters, 7 degrees south of east. So this gives it both a magnitude, and then it does tell you it's a positive number, but it also very specifically gives you a direction by giving you a degrees that you can actually describe the angle it's making with. And so if there's more than one, you may not be able to draw a triangle with it. Subtracting vectors doesn't really come up much in this class, but basically you just flip which way the arrow is pointing. So this vector would be representing B, and this would be representing negative B. It's the exact same distance. It's just pointing the opposite direction. Multiplying vectors in scalar or by scalars is pretty straightforward. If it's a positive scalar, you just multiply them and it will have the same direction. If you multiply a negative value to a vector, then that vector will just point the opposite direction and change its magnitude by whatever you multiplied it by. So if you multiply by something by 0.5, it would be the same direction it's pointing, just half the size. By negative 0.5, it would be half the size, and you flip which side the arrow would have on it. Now, this is where we're going to stop because this is the part we're going to begin with on Monday. But adding vectors by components is much more practical method of adding vectors together because you're just almost never going to be able to draw things to scale for these problems. It requires more work, but it's a lot more consistent. Because of the tail-to-tip method, we know that a single vector can be described as a combination of a vertical and a horizontal piece. Excuse me. I apologize for that sneeze. The process of finding these pieces is going to be referred to as resolving a vector into its components. And if I back up to this earlier example here, we said that this vector was the sum of these two parts. We could also flip that around. These two vectors are the two parts that compose of this vector right here. So if you were given this vector and it just points off some random direction, you could break that into there was a certain distance it had to move along the x-axis and a certain distance it had to move along the y-axis. And this is where our trig is going to come in. This is where we're going to have to start using a little bit more complex math, and we're going to have to start basically planning out our problems a lot better. But that's going to be for the next videos. This is all I want to do for this week since you guys are testing this week. If you have any questions, feel free to send me an email. If you don't have any questions, well, good. I guess I did my job. Hope you guys have a great rest of your day. This is Mr. Diamond signing off.